presentation for the morning? Not okay. Sorry. I didn't realize my presentation. So I start with a short introduction of myself about my research topic. My name is Keisuke Takahashi from today from Kagawa University, but still working at a private company of cement company. And so today I give a short talk about underwater fatigue of cementitious material, but especially used for bridge bearing foundation. And so the first of all, just a moment, this bearing foundation is the joint part of bridge. Just a moment. So the bearing part is a joint part of bridge construction, and the basement of bearing, bridge bearing, is made of cementitious mortar. And if the cementitious mortar is subject to water and repeated loading by train, the foundation is easy to be deteriorated. And this is the case of bridge bearing foundation deterioration. So this is very stable, healthy bearing foundation, but after a few, not a few, but several repeated loading, the foundation will be turned to like a mat-like state. And then at construction site or workers at construction site is believing such mechanism like this. So the first water is penetrate in the concrete or mortar foundation. And then several repeated loading to the foundation, crack occurred. And then afterwards, again repeated loading, cement turned to mud-like state. And then afterwards, in the worst case, bridge bearing is sinking like this. So next, I show some movie. Just a moment. Where is the point option? Just so this is I call initial symptom of bridge foundation. What's happening due to water penetration? And now the train passes over this foundation, and then according to train pass, bridge foundation will be, how can I say, shrink and expand, shrink and expand. And then if the water penetrate between the bridge shoe and the foundation, water can be moved between the bridge shoe and the foundation, and then water will be coming up like bubbling. So this is the case of initial symptom of underwater fatigue, and there are many places in Japan to be damaged due to such initial symptoms. And then this initial symptom going to the worst case underwater fatigue, and then the foundation can be like a mud-like state. And again, the question is, why foundation, not a bearing shoe? Because that is somehow related to historical construction method. So in Japan, I don't know exactly in other countries, but especially in Japan, until middle of 20th century, dry packed mortar was used. And what was dry packed mortar is, I was not there, but I just heard from very old persons. And at that time, there was no flowable mortar, like non-shrink mortar, but there was only cement and sand. And then cement and sand was dry mixed on construction site, and then packed by like a workman, and then water poured on the dry packed mortar. In that case, many pores will be there, and then sometimes not well hardened part will be there. So uh, such material, such hardened material can absorb more water. And then that will be the case of foundation deterioration. And next reason could be the difference of specification of bridge construction. And then the left side is Japanese bridge bearing foundation. And then right side is German bridge bearing foundation. And then fortunately, I could travel to Germany in December last year. And then that was eastern part of Germany, close to Meissen. It's Saxony of Germany. And then I found the foundation of bridge bearing, and it was about 50 centimeter or 60 centimeter height. And then in contrast, in Japan, only 5 centimeter. I don't know exactly the reason, but such specification will be related to underwater fatigue for bridge construction. So let's move on to the material side for fatigue failure. First of all, cement has a very lots of pores, very porous material. And then as the previous presenter showed, there are many small pores, like we call internal pores, and then internal layer pores, and gel pores, capillary pores. So many pores are there. And then from, I think, a few nanometer to micrometer, or more larger cases, millimeter. So cement material is very porous material. And then when we think about underwater fatigue, there are many literature, not many, but some literature are there. And then not all, but many previous studies shows surface tension theory, because wetting is filled with such small pores, and then stabilize solid surface. Solid means cementitious hydrate surface, and then interfacial energy of solid and liquid between solid and liquid will decrease, and that may cause cracks. But this hypothesis is only the case specimen is fully saturated with water. But again, cement has many pores, and then it takes time to be saturated. So when we think about such surface tension theory, we have to think about how water penetrates to the specimen when we discuss the phenomena. So it's very good comparison about my study and previous study. This is from Professor Onoue and Matsushita in 2012. They discuss about underwater fatigue affected by surface tension. But when we think about how water penetrated, for example, this is the x-axis is fatigue life. Fatigue life means time. And then the vertical line is how the material is strong due to fatigue. And then for example, this point, red point is only 20 minutes. And then blue is, I think, approximately 1.5 hours. And then green is approximately 3 or 4 hours. And then how water penetrate in a such short period. Probably it depends on the microstructure or cementitious composition. But for example, Professor Wong's research is showing how water penetrated in a short period. For example, 20 minutes, you cannot see any, not any, but you can see very small amount of water penetration. And then afterwards, water slowly penetrate. And then 4 hours, 3 hours, somehow close to fully saturated. So what these comparisons shows is here, not so much water, but here water penetrated. But when we compare such different phenomena in the same graph, that would be not fair. So that is one of my motivation to start my study. And then from here, I show some of my study. And then the first, I started with fully saturated specimen because it's quite difficult to discuss how water penetrated. And then, so we prepared 2 specimens with one specimen A is mortar saturated with water at like a negative pressure. And then specimen B is sealed with like a latex film. Latex film is #1 Japanese technology from Okamoto company. But I give a photo like this. And then in that case, specimen A, of course, fully saturated, and the specimen B is also fully saturated with water. So that means same surface energy in the specimen. And then what will be after fatigue? And then the fatigue test is like this. It's simple setup. Specimen is inside the water chamber, and then direction of force is like this. So, and then loading frequency was 3 hertz. It was close to the period of railway vibration, and the upper and the lower stress level was like this. And then the second test was penetration depth, and to trace the water penetration, we use fluorescent solution, fluorescein sodium solution. And then after a certain cycle of fatigue life, specimen was cut in half, and then ultraviolet was exposed. And then we will see the yellow color is due to UV light. And then we measured the depth of yellow colors area. So we had 2 tests. One is fatigue life, how long can be stable under water. And then the second test is how is the water penetration depth. And the specimen A is, I just show average of fatigue life, it's almost 3,000. And then coefficient of variation is about 0.8. And then in the case of specimen B, that is fully sealed with Okamoto technology. And then water cannot penetrate in the specimen. And then average of fatigue life increased. And then interestingly, coefficient of variation was decreased. So that means with sealing, fatigue life increased, but why? So I think the enhanced water motion at surface will be there in the case of specimen A. Of course, specimen B, there was no water penetration from outside, but specimen A, even this specimen was fully saturated with water, but additional water motion was there like this. So yellow colors was like a water motion. And then you can see water motion during fatigue test. So the imaging or illustration of such my idea was shown like this. So with water film, no, with latex film, water cannot go out, or of course water cannot go in. So that means water motion is very limited at the surface. But if there is no water, no latex film, water can easily go out, easily to go in. So that means microstructural failure can be promoted. And then afterwards, in the case of water, no, in the case of film, 10,000 cycle. And then if no film, 3,000 cycle. And then afterwards, fatigue failure. So that is the key mechanism of fatigue failure for my understanding. And then such idea is somehow related to the previous mechanism supported by or presented by Professor Maekawa in 2013. And then one more slide is from my side is how to mitigate such underwater fatigue. One possible countermeasure is to use like polymer cement composite. As we published with Shingo, polyurethane ether is one polymer designed by my company, and that polymer drastically decrease water uptake. And then in that case, I tested with underwater fatigue, and then that test was successful. So if you do not add polyurethane ether to the cement or mortar, water uptake during fatigue test was very high, but if you dose polyurethane ether, the water uptake will be maybe half or less than half. And then that could be main reason to enhance the fatigue life with the presence of polyurethane ether like this. If you do not dose 3,000, but if you dose 12,000, and then coefficient of variation is also decreased due to the presence of polyurethane ether. Such way can be a countermeasure for underwater fatigue. So today I show very short information about my study, but this has been submitted and under revision of CBM paper. But fortunately, you can get download the preprint version of CBM paper from this website. And I'm very happy if you have any question for this presentation. Thank you very much.
For your presentation. So let's move to discussion. Do you have any question? Ali?
Thank you. Thank you for your nice presentation. I was wondering, if you come back, please, to the slide 11. So perhaps also it's because when you have exchange of water, you will have a gradient of swelling and gradient of drying shrinkage that can lead to initial stress inside the specimen and even cracking.
Initial swelling or deformation is almost same between A and B. And what do you mean?
What I mean is because you have a gradient of water content inside the specimen.
In the case, there's no gradient.
Because water can go in, can go out. And we can see, I think it was in the previous slide, we see that you have, with the green So it was the slide 10. So we can see water which is in the surface, and perhaps even a crack. Is it two cracks at the top?
No,
Because it's not uniform.
this is not crack, just water penetration.
Mhm.
And what this figure shows is already this is not, I think this is not water gradation. This is just showing water motion
Mhm.
from inside to outside.
Mhm.
And then for my understanding, water, I think like a gradient of water content is totally same in the specimen, because before testing, I put the specimen in the negative pressure chamber
Mhm.
to how can I say, to penetrate fully
Mhm.
the water. And then I just understand there was no weight change after negative pressure water chamber. So that means still hypothesis, but that means there is no water penetration, or I can say there's no space to water go in before the testing.
Mhm.
So that means this yellow color or green color just shows water change. Water. So for example, here, some place water go out and then water go in. So the outside water turned green.
Okay. Okay. And for the specimen A, so there was 0 cycle, so it means that the specimen failed
Specimen
failed
failed
at the
before
beginning.
testing.
Okay. Thank you.
Question. Question from the Zoom audience? No? Okay. So if so, thank you for Dr. Takahashi, your presentation. Okay, let's move to the final presentation in the morning session. Yeah, Marofi, could you give your presentation? Yeah.
Thank you. So hello again, everyone. Today I'm going to present some work I've been doing on the durability assessment of some eco-concretes or hemp-based concretes. So it's a bit different than what has been presented before. For those who don't know, hemp is like a vegetal fiber that is very available in France. So first, I'll start by setting up the context. You all know that the construction sector has a very heavy environmental impact, since it is responsible for 35% of the total energy consumption and 38% of CO2 emissions. It's also responsible of the consumption of more than 50% of natural resources including sand, gravel, limestones, for example, that are all components of concrete manufacturing, as you know. This highlights the need to use alternative building materials that can be based on vegetal aggregates or recycled aggregates, for example. There's a large variety of bio-based or vegetal aggregates or recycled aggregates that are already being used in France. Those I posted in here are the most commonly used in France, but this list is really not an exhaustive one. And there's a lot of other materials that are used. The most used ones, as I said, are hemp concrete, for example, or hemp in concrete, flax, which is quite similar to hemp, straw, which is also a vegetal aggregate, and recycled polystyrene, for example. There are a lot of recycled plastics that are being used, actually. But the issue at stake is that these materials are relatively new. They are not being used since a very long time. So we don't really know a lot about the evolution of their functional properties or about their durability in different climatic conditions, for example, which limits their use in construction or in buildings. In this work, I'm focusing on hemp concrete, which is roughly composed of hemp chives, some kind of binder, and water. I deliberately did not put any mixed proportions in here because depending on the use of the material, the quantities can vary like a lot. Hemp concrete is mainly used as fill-in material in walls with wooden structures, for example, but it also can be used as pre-made blocks, like you can see in here, and also sometimes in roofing elements. And the question that always rises, even if in France it's been used in the last like 20 years or so. But the question that rises is the question of its durability. So in this work, or in our work, the studied composition is aimed to be as floor type applications, or what we call top-in in the floor. So the mixed proportions are explicit in here. So it should be 50% binder, 40% water, and 10% only of chives. Two types of chives have been used. And also two types of binders. Regarding the chives, the difference is mainly in the size. As you can see in here, those on the left side are quite bigger than those on the right side. Regarding the binder, we used both cement, but also hydraulic lime, which is the most used binders with this type of vegetal aggregates. It matches very well, actually, with the hemp or flax chives and gives pretty interesting mechanical performance. In previous works, multiple works have tried to assess the durability of hemp concretes through experimental, what we call accelerated aging protocols. The first ones are all based on accelerated aging protocols that are really very severe and more aggressive than the real conditions of the materials during their life, actually. The second type of protocols are really not severe, but they do not really represent the real humidity and temperature variations of a building, for example. So what we propose in this work is to evaluate the durability of hemp concretes through a different protocol or through a different approach, which we think would be more representative of what materials undergo in their life cycle. So what we propose is a partial immersion instead of a complete immersion, as we can see in the previous works. Indeed, when they are in buildings or building walls, undergo only partial immersion through capillary rise. So that's why we chose only partial immersion and a moderate temperature variation. So after the concrete manufacturing, the samples were stored during 28 days before submitting them to the aging or the accelerated aging. So the laboratory protocol, as you can see, is based on 8 successive cycles of partial immersion and then drying. The partial immersion was at room temperature at 25% degrees and lasted 2 days. Each cycle lasted 2 days, and the samples were immersed at 8 millimeters. The drying part lasted 3 to 5 days, depending if it was whether a weekday or a weekend. And it was in a ventilated oven at 40 degrees. And for both the immersion and the drying, the samples were the side of the samples were covered to ensure a unidirectional flow. Hemp concrete properties were determined before and after the accelerated aging. So the thermal conductivity was determined using the hot wire method, as you can see in here. The water absorption, sorry. The water absorption coefficient was determined following the standard, an American standard, because we don't have a European one for this kind of concretes. But basically, the protocol was to immerse dry samples, completely dried samples at 3 millimeters of height and measure the water content during different times for 24 hours. The compressive and flexural strength were determined according to the European standards. So as preliminary results, because the work is still ongoing, we can first see that for both compressive and flexural strength, the lime-based materials have higher values or higher results than the cement-based ones. After the aging, we can see that for all formulation except this one, the compressive and flexural strength tend to decrease. The exception was the combination of cement and the large-sized shapes that did not show any significant impact after the aging, either for compressive strength or for flexural strength. And I honestly don't have an explanation for that yet. Regarding the values of compressive strength, it's in good agreement with what we can find in literature. It goes from 0.6 to 3.6 megapascal for compressive strength, and in literature it's between 1 and 3 megapascal. The decrease for compressive strength was between 15 to 40%. And in previous works, it was even higher because it was around 50%, between 50 and 55% decrease. In terms of flexural strength, it was even higher since it decreased from 40 to 60% after the accelerated aging. Regarding the thermal conductivity, so here I'm plotting the thermal conductivity. The results of reference state materials are slightly higher than what we can find in other works. But the difference, we think, could be linked to the time of drying or drying time. We tested our samples 28 days after manufacturing, but in previous works, they tended to wait until 80 days before carrying out the tests. We only waited 28 days. So maybe this is the cause of the higher values for our work. Concerning the results, the obtained results are directly correlated to the density and the porosity, but that's another thing. They show the same trend as we can see, and this is also in good agreement in literature, where thermal conductivity varies in the same way or increases in the same way as the density. In general terms, the aged concretes all showed a decrease in thermal conductivity, except the combination of cement with the large-sized chives that shows a slight increase, but it's not really significant because it's included in the error bars. So I would say it didn't show any significant impact after the aging. So for all formulations, the decrease in thermal conductivity was between 14 to 30%, which is quite higher than previous works where it only decreased by 6%. Regarding the water absorption, we can see that all concretes exhibit the same tendency. Even the combination of cement and the large-sized chives, which actually shows the biggest variation after the aging. It's the green one. So I was saying, yeah, all concretes exhibit a decrease in the water absorption coefficient, and this decrease is actually a good thing because water absorption is a good indicator of durability. And the higher it is, the lesser the durability is. The decreases can go up to 75% for the CHASB formulation. These results may seem inconsistent with porosity that really increased after the aging, even if I didn't present the results. But actually, what we can see in previous works also is that the increased porosity is the intraparticular porosity, and what's really working with the water absorption is the capillary porosity. So it's quite different, and we think that the aging may create new porosities, intraparticular porosities, but may crush existing capillary porosities, which could explain the increase in the porosity value, in the total porosity value, but the decrease in the water absorption. So we also did some observations under a microscope to highlight any microstructure changes in the surface of the materials. We could see that there are new cracks that appeared inside the aggregates, and before the agent, it was merely at the interface between the matrix or the binder and the aggregates. We could also notice the expansion of already existing cracks, but always on the interface between the cement and the aggregates. And for lime-based concretes, we noticed quite interesting things because we could see that the fibers or the aggregates changed colors only for the lime-based formulations, as you can see here and here, for example. And that even the lime was attacked, and there were some kind of mold appearance or mold growth in the binder for lime-based formulations. In previous works, they found out that the vegetal aggregates can liberate or can liberate some molecules that attack the cement, and we think it could also attack the lime. So, as a conclusion, but also a lot of perspectives, we tried to suggest or to elaborate a new aging protocol which would be closer to the real aging of building materials and less severe than what we can find in previous works. The results may be due to the microstructure modification, in particular, especially the intraparticular porosity and the capillary porosity. We should have some more precise microstructural study to understand the real microstructure variations of the materials, and maybe study other formulations to assess the influence of different aggregates, for example. Regarding the porosity measurements, I didn't present the results, but we used the water intrusion porosimetry, which is not the most precise method for these kind of materials. So maybe we should do a more relevant porosity measurements, maybe using microthermography. And thank you for your attention.
All your presentation. Let's move to the discussion. Do you have any questions?
So thank you very much for this presentation. So this material is maybe not new to me, but I'm far from being specialist. So I have some questions. First of all, you use the term that it's hemp concrete, but from what I see, the addition of aggregates, it's not so as important as in concrete. It rather looks more like mortar, I would say, given the amount of the additions and also the size. So if you could please enlighten me a little bit in this regard.
Well, I also think that the term concrete wouldn't be the most suitable one, but also because we don't have, for example, any sand or
Yes.
any small aggregates. And what I forgot maybe to mention that the formulation or the mixed proportions I presented are a mass ratio. So this is why you could think that there are not a lot of chives, but since they are really light, if you convert to volume ratio, you would have much more actually.
Okay, and do you consider grading somehow? Because you had two grades, but for two
Yes.
different mixtures, but like analogically to concrete, do you consider grading?
Yes, for each chive, we do consider that, but as I said, this is still ongoing, and these
Okay.
are only preliminary results.
Okay, thank
But
you. And
it's actually-
the second question,
And it's
because I
very-
don't want to steal.
And just for information, it's very hard to do grading in this kind of aggregates.
Oh, I can imagine. I can imagine. And the second question, because when you were showing your result, you were always comparing to other studies. But to my understanding, you are using totally different protocol. And you said that the others, to which I assume you are comparing, are either much harsher or much lighter. So can you comment, at least briefly, how your results, because when you were comparing globally, but if you would also divide this comparison into harsher and lighter, how your results are placed among these, like, are they in the middle or they are totally outside of the range?
No, I would say they're more close. They're closer to the most severe works that have been done. So it's
Okay.
more closer to that.
Okay.
Even if the protocol is not as aggressive as theirs.
Okay, so it means that your conditions are similar to the real ones, but those which are much harsher than real ones are still close. So
Yes.
it's not all
Yes.
exaggerated too much. Okay, thank you.
So thank you for your presentation. I didn't understand your mix design of your mortar or concrete. I don't know exactly. Could you show me the mix proportion? I
This.
don't know what is the binder of this system.
Actually, I have 4 different materials
Yes.
or formulations. So I mixed the 2 binders, so hydraulic lime and cement,
Okay.
with 2 different chives. So I have 4. Each time I have lime plus this one and lime plus this one, and same thing for cement.
And then chives, is that binder or aggregate?
This one?
No, that top one.
These?
Yes.
No, these are the aggregates.
Yes. Okay. So the binder is like a simple mixed with limestone powder and cement.
Yes.
Right? Okay. And then the aggregate is such how can I say shapes? It's only aggregate. Shapes. I don't know the pronounce.
The chives.
Chives.
Yes, yes. Only these are actually the vegetal wastes
Okay.
that they are called chives that results after the all the other manufacturing of hemp.
Okay, without sand, without any like a hard aggregate.
No.
Okay, and then the one more confirmation is what is our aging protocol? Aging protocol is only
This one.
Yes,
Oh.
water.
So it's a partial immersion in water. It's 8 millimeters high.
Mhm.
And then we dry it for 2 days, and then dry it in the oven at 40 degrees.
Okay, so you focus on like a water movement from inside to outside, like a humidity process.
Mhm.
I think carbonation process will be there for the aging protocol because CO2 will be around the specimen. So that means if you dry the specimen, the specimen will be carbonated because you have Portland cement inside. No?
I didn't, or at least I'm not a specialist of carbonation, but at least I didn't notice any changes due to that. I think for lime, it shouldn't happen.
Yes,
Carbonation
but
shouldn't
you have
happen.
Portland cement.
Actually, it's not Portland. I don't have its prompt natural cement.
Prompt natural cement.
It's a bit different. I don't really know its composition, but I can find it. I'm sure I can find it in my.
Okay. So I just thought that is a Portland cement. But
No, it's not really. But I didn't notice anything. But again, I'm not a specialist. I didn't really focus on that.
Right. Thank you.
Thank you for sharing your research with us. What is the intended application of this material? Is this indoors, outdoors? This is one question. The second is, can you comment on the sustainability? Because I see that you have a lot of binder in this material. So the carbon footprint of this material might be high, particularly if you use hydraulic lime as binder. So if you could comment on that, please.
Okay. For your first question was about the applications. Yes. As I said, it can be. It's mainly used as fill-in, as in walls with wooden structures, but it also can be used in roofing elements, for example, or for top-ins on the floor. It's mainly used for thermal insulation properties. And also for hydric or humidity regulation purposes, because these materials are known to store humidity when it's very high in the building, and then restore it when it's lower. And for the sustainability, so I didn't do an LCA. But even if the as I said, the mixed proportion is it's in mass ratio. So even if it seems that it's a lot, because we have 50% of binder, but in mass quantities, it's the same thing as that we can use in a regular cement, in a regular concrete. So it's not really more than we use for regular concretes. And the idea here is to limit the overexploitation of natural resources such as sand, gravel, etc., by using other aggregates. In France, these aggregates are really just waste. I mean, the hemp fibers are used in pharmaceutical industry, for example. And these, what we call chives, are really a waste. So it's a waste. It limits the use of other natural resources. It can store CO2 because it's vegetal particles. And it can improve thermal insulation. So less air conditioner.
Yes, so some questions to have, but due to time limitation, and then we need to go to lunch. So I would like to close the morning session. Thank you very much again. Okay, from now we would like to have the lunch break for attendee in person and the Zoom participants. So we will start about 1 hour later in Japan from 2 p.m. Thank you for your joining, and then let's have the break. And then Dirk, are you there? So I'm put you the panelist. Dirk, could you? Okay. Okay, Dirk, can you
All
hear
right.
me?
All right.
Oh.
It worked. Hi.
Okay, now you are here. Good morning.
Hello. Good morning.
Sorry, we are going to lunch, but okay, so
No, that's all fine. Have a good
Okay.
lunch. We see you later.
okay, you may
Recording stopped.
break. Okay, thank you.
Yep.
Just the questions of Dirk will be after the lunch and then
Sorry, yeah, yes.
Okay.
Yeah, we will go the lunch place for Chijiba-san. Follow him. Agnes, I understand your presentation order. Dirk will present soon after the lunch, and then you keep your position.
Okay,
I'm sorry,
thank you.
I misunderstood.
Yes. Hello, everyone. I guess you met me, Miguel Lasanha. I'm helping the organization of the event, and Shingo Asamoto has instructed me, because he's getting one of the invited speakers from outside. I will start the session now, and for the sake of punctuality, it's 2 p.m. Japanese time, so we would start. And there was a slight change in the program, because we had a unavailability of our colleague Dirk Schlick in the morning. Forgive me, sorry. We had the unavailability of Francisco Canavares in the morning, but now in the afternoon we also have a change. Dirk Schlick needed to be the first to present, as opposed to the current program. But the presentations will be exactly the same, but with a switch between the presentation of Dirk Schlick and I think it's the one by Nagai, right? Yes, confirmed, Dr. Nagai. Thank you. So yes, basically we are going to have now the presentation by Dirk Schlicke, and then in a slot you would present.
Recording in progress.
So I would invite Dirk Schlicke. Are you listening to me? To us?
Yes, I'm listening. Yeah.
Okay,
you
we
hear
are
me?
just adjusting sound. We'll put your face in camera, probably. We just click here, the middle one. Yeah. Yeah, if you can open camera, we can see your face. If not, no problem.
At the moment, it's because you have stopped the camera. It says.
mm, maybe. Just no.
But
It's
if you
still
don't, if you don't mind, I can also simply share the screen, and there's a picture of me.
No. He will share the screen. So if you cannot activate the camera, I think we go on as it is, because from here you seem to have all the necessary authorizations.
It says host stopped camera.
Okay.
I don't know. Can you see the screen at least?
No, not yet. Can you share?
Oh, it's shared, and it's green for me.
But now you are sharing your own. I'm not helping much because everything is in Japanese. Oh, he's the administrator. Okay. Oh, be careful. Please try to share the screen.
I think it's sharing.
Sharing. Okay.
So I will simply try it again, if you wish.
Okay. Now it seems to be working. And the camera, could it be managed or not?
Still not. Still host stopped camera.
But I think we can go on.
At least you can see now my
Yeah.
screen, yes?
And your picture.
Okay. Yeah. Hello, everyone. I'm glad that you managed to move me a bit, because I need to go somewhere else today, and that's why I'm also not in person in Japan. It's a pity, but at least I'm happy to share some thoughts of mine with you here in this workshop. And today I would like to discuss with you what is the crack opening in reinforced concrete. We did some advanced 3D FEM analysis on this, and this is what I'm going to show you. Why did we do this? Because there's a great variety of models for crack width calculation available, but there are partly questionable approaches for crack width calculation in the standards, but also in the scientific contributions. So there's, as you see during this workshop, probably there's a lot of calculation models available, but if you look at them, this is often not really clear what What is the main idea behind it? What are the drawbacks? What are the simplifications? Anyway, what you can see is there's a great importance given to statistical analysis of experimental observations. So we have often the discussion, how does the model perform in comparison to experiments? On the other hand, mechanical fundamentals are often significantly simplified in the calculation models, if not even violated. So on the one hand, we want to compare with real data coming from experiments. On the other hand, yeah, we allow ourselves to have significant simplifications in the models in order to make it practical or understandable, transparent, and so on and so forth. But at the same time, we sometimes violate mechanical fundamentals. There's also some ambiguity what the results of crack width calculation models even mean. So there's the question, is the calculation result referring to a maximum crack width to be found on site? Is it a 5% quantile of what we can found on site? Is it a mean crack width? But there's also the question to where is the crack width calculated referring to? So is this a surface crack width? Is this a crack width at the reinforcement? What is this? And to get a bit into the topic closer, we can look at the experiment of Borosnoy and Snobly from Hungary. And they made a reinforced tie, as you can see here. There's the concrete cover. This is the rebar already sawed. So cut the specimen, they tied it apart, produced a crack, filled the crack with epoxy, and then they cutted it. Something similar was done 40 years earlier by Goto. But here you see also the crack width over the concrete cover. And we can see at the surface level, the crack width is very small, like 0.1 millimeter, and it grows significantly to the surface up to 0.45 millimeter. As said, there's more than this one experiment. There's, for example, another one from Hussein and Ferguson, 1973, so also quite old. And they also made measurements over the concrete cover. And you see here, for example, distance from bar surface 0 to 75 millimeter cover. The increase here is linear, but I guess they have only two measurements over the height, so they made it then linear. They show that the crack width increases linear over the height. As you can see here, it's the same. Right, so from 0.1 to 0.45, here increases from 0.05 to, for example, 0.15, and so on, for a given steel stress. There's another contribution, namely from, these experiments indicate significant change of crack width over the cover, obviously. There's another contribution from Professor Beebe from the UK in the discussion, the influence of the parameter diameter versus effective reinforcement ratio on crack width. And there he gave us this scheme where he showed a bar, there's a crack, and you see here some crack deformation over the height. And he assigned in this idea 1/2 of the crack width to sort of a slip. He called this internal failure. And the other half of the crack width, he said, this comes from the shear lag. So he concluded the surface crack width is significantly affected by shear deformation of the concrete cover. However, behind this theoretical model idea, there is no experimental or numerical evidence. So this was an assumption. If we go further and say, well, okay, what exactly is now the crack width? We saw this is changing over the concrete cover. It must be smaller at the reinforcement. We can call this a crack width at the reinforcement. It's larger at the surface. We can call this a surface crack width. We saw there is some shear deformation, which is here marked in green. And overall, we can also say there is some sort of a global opening subject to compatibility of the member. So overall, the length change of the member, delta L, must be equal to the global crack width, so some uniform opening, plus what is happening in the concrete over the length. So there is a surface crack width, crack opening at the surface, a crack width at the reinforcement level, very small one here in the near of the reinforcement. But there's also a crack opening assuming uniform deformation of the crack edge. If we look closer, we can see, well, this real crack edge deformation is subject to what we call internal cracking at the ribs. We have a load transfer from the rib to the concrete. The concrete is a porous and very fractile material, which gets internal cracks due to the contact with the ribs. If you pull out the bar, the rib gets into the concrete, makes internal cracking, as the deformation from the concrete is not possible without cracking in this size. And overall, if you make compatibility over the length, over all lengths, this must be, of course, be equal over the height. So if you have a lot of internal crackings near the reinforcement bar, there's of course no real crack opening here at the reinforcement. And if you go away from the reinforcement, you see, well, the internal cracks do not proceed over the entire concrete cover. Of course not, because this gets weak due to the small crack, then strain gets a bit smaller. This is already some stiffer, and the crack growth into the concrete gets smaller. And if you look on the primary crack, you see, well, if there is no internal crack at the surface region, of course, there's also no crack opening. The crack opening of the primary crack must increase. Otherwise, you would not fulfill compatibility. This is also was measured with here some X-ray. This is from German PhD, where you see this crack root. There's the primary crack. Of course, there's some smeared because it's X-ray through the entire bar, and there's some shading in this. Anyway, what you can see is there is these internal cracks very pronounced near the primary crack, and the more you get away from the primary crack, the internal cracks also mitigate. What we do now in calculation is not calculating these internal cracks. We simplified this all, the weakening due to internal cracking, by a sort of a spring, so force deformation relation. And we assume here uncracked concrete. So the internal cracking is represented by a weak spring, and external, or the primary crack, is represented in a primary crack, which has of course no deformation over the height of the concrete cover, since we apply the spring from the reinforcement to the center of gravity of the concrete cover. The shear lag, which refers to solid material, shear deformation of a solid material, can then of course occur if you apply these bond springs at the contact area between reinforcement bar and the concrete cover. Then you get some shear deformation as shown here, which can of course increase the surface crack width. The first mechanism, that's not the first mechanism, but the real mechanism can only be obtained with 3D FEM simulations with concrete fracture, actually. And the other simplifications refer then to analytical models based on bond law. I mean, of course, you can also put this in a 3D model with a bar, and you put the spring interface between this, and then you can also simulate this, but you can also represent it with the analytical solution. We made these 3D FEM simulation of the model for a tie. You see a reinforcement bar in the middle and a rectangular concrete cross section around it. The size of the cross section is 2 times the concrete cover plus the reinforcement diameter. And the model, in terms of savings for computational costs, we used only a quarter of it. It looks a bit like this and was done with Athena and also published, however, only in German, unfortunately, but I will help you through this. We have there some nonlinear concrete volume. There are symmetry areas using symmetry in 3 directions. We have a discrete reinforcement bar here in blue. We have a free surface for the first crack. So the first crack was not occurring due to fracture. It was already included in the model as a free surface. And the load application occurred here in the reinforcement bar. Meanwhile, the lines over which results were analyzed are given here in yellow. This means along the length of the member here in the center of gravity and over the height of the member also in the symmetry. If you look into it, you can see there's this nonlinear concrete volume. We have a nonlinear reinforcement element, discrete ribs on this. The contact area between the both is a more Coulomb law, and the lines over which results analyzed are plotted here again. The reinforcement itself is also 3D, including the ribs, even included that the ribs is not going around the entire bar. If you look at results, you see in this quarter modeled, if you pull on the reinforcement, there's some internal cracking, it looks like, and after a certain length you get another crack and another crack and another crack. But for this you also need to increase the force. So if you start pulling, you start having only this opening of the first crack, and then the force is introduced back to the concrete so that the steel stress decreases. After increasing the force, you get a second crack, then a third crack, a fourth crack. The occurrence is not controlled via a scatter of tensile strength. The occurrence is only some random occurring, even though there's no scatter of tensile strength. And after producing all 4 cracks, you see this crack is not really open. You also we get some force transfer over the crack still. But if you increase the force still, then all cracks are open. The steel stresses in each crack are similar to each other. And in between the cracks, we have the tension stiffening effect. This is how it looks like if you look a bit closer. And what you can see here is this internal cracking at the ribs is also presented by the fracture of the concrete. And we can also obtain the crack width at the reinforcement and also at the surface. Plotted in a diagram for the half system in length direction, you have the half crack opening in millimeter over the height. You see this distance from the reinforcement. It's very small crack width, and then the crack width increases, as we saw in the experiment from Borishnaya and also from Ferguson. Comparing to an analytical model using slip-dependent bond stress, so using now the springs in a hand calculation, we can use a bond law in the form of bond stresses over the length must be equal to a constant depending on the slip and the slip over the length. These are the parameters, and this is how it looks like. We have a bar or a tie, a reinforced concrete tie. We pull it apart, we get a crack, and from the crack, the concrete slips in the direction to the uncracked material. So here is the largest slip, and then the slip decreases until you have compatibility between concrete and reinforcement. And on this side, the same behavior, but with the minus. The local bond stress due to the slip, so the material is slipping, the springs are activated, you can say so. We have bond stresses starting at the crack with the largest, and then it decreases, decreases, decreases until there's no slip, and then there's also no bond stress anymore. This is usually averaged with a mean bond stress, but does not mean that this is a constant bond stress for all crack widths. This is only a mean bond stress over the slipping length. The energy must be, of course, in equilibrium. So this means what we have at below the surface of the curve of the bond stress, the area must be equal to the change of the force in the steel bar. And from this, we can obtain now the steel stress distribution. It is the steel stress at the crack is the largest, and that decreases, decreases, decreases due to the bond stiffness. And when the slip is zero, of course, the steel strain and the concrete strain are equal to each other. There's also a force equilibrium in between, which means that the change of the steel force must be equal to the deformation of concrete for the same force. Of course, the bond law you saw here is then applied with some known parameters from the German code. And using this, you see the local steel stress over the slip performs like the red dashed line. This is what the bond law shows or gives we use here. And there's, of course, other bond laws. There's one in the model code, which is the blue one here. You see for normal bond conditions in the German one is the same as, almost the same as in model code, that we have also the distinction to better bond conditions, then it's better here. And there is no good bond conditions in model code, then you have, of course, poor stresses. This slip can be related to a crack width, namely if there's slip to one side, is also the slip to the other side, and 2 times the slip is the crack width. This can then be averaged to a mean bond stress in the slipping lengths. There's a numerical approximation presented from Thur and König, I think in 1985 or something like this, which can be applied. And if you use this, you see the mean bond stress increases with the crack width. Small crack width, small bond stress, large crack width, larger bond stress. And if you change the crack stage to go from single crack stage to stabilized crack stage, this increases additionally. What we usually use in the calculations is a constant mean bond stress of 1.8 FCTM, and you see, especially in the area where we often want to control the cracks, so between 0.2 and 0.3, it depends significantly on the crack stage, whether this is a good approximation or not. And if this crack width gets smaller, it's actually very worse assumption, very bad assumption, what we have in the code. Anyway, in general, we calculate the crack width with the strain difference times the slipping length. And for maximum crack width, we of course use the maximum possible slipping length. And then you can calculate the crack width for single crack stage and stabilized crack stage using the slipping length and crack width dependent mean bond stress. And this is, as I showed before, not 1.8 FCTM. So here we apply a slip depending bond stress. And of course, if the crack width is not known, we get here some iteration. But if the crack width is known, you can simply put here like the crack width criteria, then you get the bond stress for the crack width criteria, and you can apply this directly in design solutions. But to which position at the concrete cover does the calculated crack width refer to from an analytical model? Is it the surface crack width? How about the significance of the shear lag effect? BB said this will increase our crack width by a factor of 2. So this is some reasonable increase. We must check. If we compare now our analytical solution, this is in gray, with the FEM simulation, which is black, we see there's kind of a very good agreement between these results for single crack stage almost independent what bond condition we choose. But if we go for stabilized crack stage, we see, okay, our experiment or our simulation, this was rather a small diameter, so we must calculate with better bond. We have also an acceptable agreement. So for me, honestly, this was a surprisingly good agreement. If we go further, we can now check the crack opening over the concrete cover, and we see here for a concrete cover of like 25 millimeter, the analytical solution with a bandwidth of good and normal bond compared to the FEM simulation, which is this curve, suit quite well or compare quite well to each other at the surface. Same happens if you have an increase of the steel stress, which is then 300 Newton per square millimeter, comparable to surface life conditions usually. This at crack formation, this is for surface life condition. We also have a good agreement. And if we start to change the configuration, so we have different diameters, different concrete covers, we also see that the analytically calculated crack width refers rather to the surface crack width of the FEM simulation than to the crack width at the reinforcement bar. Overall, analytically determined crack width refers to the surface crack width independently from the concrete cover. And this is very important because all our codes, they have an additional cover effect. If you remember, there's some additional cover term in the slipping length determination, which is in fact not mechanical. This is only due to the statistical variation and falsification of the bond stresses in the calculation formulas. So in fact, we have no additional effect of the concrete cover on the crack width. This means also the shear lag effect is almost zero, so that the idea of BB was not confirmed by these investigations. Overall, I tried to define what is a crack width and related mechanisms were discussed. I showed you a 3D FEM simulation of cracking with respect to internal cracking. I showed you that using the bond stress trip relation in an analytical solution is possible and gives a rather sound analytical solution. We compared the two approaches. They indicated a good agreement, and the practical application of maximum crack width calculation is therefore reasonable. Overall, you can go and use this already on a homepage. It's called crackcontrol.com. Here's some explanatory note. I will not go through this now due to time reasons, but what you can do, you can fill your data in here for the concrete compressive strength, tensile strength, elastic modulus, some bond parameters, the cross-sectional area, reinforcement, we have 12 millimeter diameter, 4 bars. This is the steel stress we are going to calculate. And if you go calculate, as I showed, iterative solution, the homepage will do everything for you and can gives you here now the local slip for the experiment. You see the bond stress evolution over the length. The black line is the mean bond stress. The gray line is the 1.8 FCDF assumption, not very well fitting. And then you can see here the local steel stress. And the resulting crack width for this configuration would be 0.13. Also possible for stabilized crack stage. For example, you see here larger crack width, of course, different slipping, and there in this situation you have quite a good agreement, but this is usually no surface life condition. All right, with this I'm at the end of my presentation. I can simply show you that you get also some good comparison with databases. We have also database on crack width, and yeah, with this picture I want to finish my presentation. Correlation is not causation. We always need a good mechanical model. If you have questions, I'm happy to discuss with you. Thank you very much.
Okay, thank you. I don't know if we have extra microphone. No. Anyway, let's start with questions first. Oh, we do have one. Let's see if we don't have echo.
So thank you, Dirk. This is Farid.
Ah, hi, Farid.
Hi, Dirk. Very nice presentation. Can you please come back just to the previous slide? You know, when you compare, experimental results with calculation. So you were very fast on that, but for the bending, it seems that you every time you overestimate. That's right, the crack opening.
Yeah, it's
Do you
not
have an explanation?
overestimating.
Or?
Yeah, sure. It's no overestimation. This is an experimental crack width. And
Mhm.
experimental crack width means not that you have the theoretical possible maximum crack width. This is already subject to scatter. So you will, of course, you have a maximum crack width in your experiment. But this does not mean it's the maximum crack width you can obtain in the worst condition. So maybe here you have already some relief of crack width due to scatter. But when we calculate, we really calculate the maximum possible crack width. So actually you should not look that everything is on one line. We also
Okay.
we only need to check that everything is on this side of the diagram. You know, this is then the prediction idea.
Okay. Thank you, Dirk. It was very
Otherwise, we must run calculations with scatter of tensile strength, and then you need by random field theory, for example, like a Monte Carlo simulation, and this would, I would say, from computational time, last over a couple of years. You know, this is almost impossible. But this is the reason. The reason is we calculate, we compare experimental data, which does not necessarily give you the theoretically maximum crack width, with a calculation which shows you the maximum crack width.
Thank you, Dirk.
Yeah, thank you, Farid, for the question.
Okay, thank you. We still have time for one more question at least. Oh, just there.
So thank you very much for your great presentation. I'm Nakara from Hiroshima University. So I have so you can keep the same slide. So I have a related question. So I clearly understand the concept of the simulated crack to discuss a possibility or the maximum possibility. But in the left-hand side figure of your slide, attention, I found the one variation. So yes, so could you explain the idea? So for the bending, so I clearly understand your concept, but how about pure tension mode?
In pure tension, we need to distinguish between single crack, which is quite well fitting in pure tension. You see, single crack is always above. It looks not bad. It's the orange. So there's a mistake, and not a mistake, but unfortunately there is one dot from result dot destroying the legend, right? So single crack means orange circle. So this works quite well with prediction. And as soon as you come to the stabilized crack, there is sort of I would say confusion in the results. We still have it here in the result. Maybe I should remove these experimental data, because the definition of effective concrete area, which enters the calculation, is not very clear in the case of these experiments. So this type of experiment is not really representative for what happens in reality, let's say. But there is some confusion with the effective concrete area, and I calculated with the small concrete area from the Eurocode definition. But if you use the concrete area, the entire concrete area all the time, also in the stabilized crack stage, then it would also shift over this. Maybe this is, I don't know if you can understand it by this. This probably needs a bit more discussion. But actually for single crack stage, this works quite well, as you see. For stabilized crack stage and pure tension, you should, or you must change. Where is it? Is the calculation. There's some effective reinforcement ratio. And in this particular situation, if you change this here to the entire cross section, you would get good results also for the recalculation of these experiments.
Thank you very much.
Yeah, I hope it. Maybe you write me an email, then we can follow up with this discussion. All right. In that case,
Yes.
I think no further question, right? Was there more question?
Also to keep the program. So we would thank you very much, Dirk. Of course, you can stay for an exciting presentation. By
I need to go. Unfortunately, this is the problem.
Yes.
Yeah.
Have a great meeting in the meantime. Okay. Thank you.
Thank you. See you tomorrow. Enjoy your time there. I would be
thank you.
Happy to be with you, but impossible. Bye bye.
Okay. Bye bye. So on next presentation, we have we are following the same topic, and we are basically delving a little bit into the influence of transport in cracking. And for that, we have an expert, Professor Farid Bambojema, who will be delivering his nice speech. And I think that's it.
Thank you.
The floor is yours. I'm sorry, a little bit echo.
Thank you, Mr. Chairman. Yes, the topic is quite similar to the one presented by Dirk Schlicke. So you will find also simulations on concrete time. But in my presentation, I will focus a little bit on the effect of drying shrinkage. And the objective is, like Dirk Schlicke, is to predict crack openings and regard especially to durability. So it will be related to transport properties. Thank you. Thank you. So if you look to the effect of drying, you will find that drying may have a positive effect or negative effect. So for instance, when we look to the permeability, especially the permeability related to gas, of course, so the permeability is equal to 0 if the material is completely saturated. And when you dry the material, the permeability will decrease. So sorry, I don't know if there is an echo somewhere. Or... Well, I'm trying to find a place without echo. And for this diffusivity, it depends. So if you are looking to the diffusivity of ions, so if you have water, you have the most important value of diffusivity. And when your concrete is drying, the diffusivity is decreasing. So it's quite clear. But if you look to concrete properties, mechanical properties, you will find whatever you want. So most authors find an increase of mechanical properties due to drying. I will explain why a little bit further. But if you look to results of Jean-Michel Torrenti, so he was my PhD supervisor, very nice guy, he finds that in contrary, a decrease of mechanical properties with respect to drying. Regarding Young modulus, most of the time you find a decrease related to damage, but sometimes you may have a small increase. And for tensile strength, you will find whatever you want also, a decrease, sometimes an increase. So drying shrinkage and dry creep is quite bad if you are looking to the effect on the pre-stress loss, but creep can be good, especially when you are looking to the prediction of shrinkage restraint. And also it will affect concrete pathologies. So why we have a negative effect of drying? So drying is quite a very slow phenomenon. So diffusivity related to the water migration is about 1,000 times lower than the thermal diffusivity. So when you dry the specimen, so you will dry at the beginning the surface of the specimen. So you will have more drying shrinkage in the surface than in the core. So you are restraining shrinkage of the surface. So in order to restrain the shrinkage, you should induce tensile stress. So we will find that you will have tensile stress in the surface and you have self-equilibration. So it is self-equilibrated by compressive stress in the core of the specimen. And you know that tensile strength is quite low in concrete. So most of the time we have cracking, and cracking can be observed by eyes or also by digital image correlation. So we can say that this cracking at the surface will decrease the mechanical properties and will increase the transport properties. But do not forget that drying can be positive. Perhaps you have been as a kid or playing with your kids on the beach. So in order to build a castle. So if you have a lot of water, no, it's not possible. You will have something which is quite a liquid. And if you have no water, it's just particle of sand without cohesion. So mechanical property will be less important. So you have an amount of water that is very good, and it will increase the mechanical properties. In fact, if you are looking to the mechanisms of drying shrinkage, so capillary pressure, disjoining pressure, etc. So since the material is shrinking, in order to shrink, you should have compressive stress. So you have internal compressive stress that gives rise to drying shrinkage. So it likes like a press stress, so it will be positive. So that's why in the literature, you may find an increase or a decrease of mechanical properties. It will depend on the intensity of the compressive stresses related to these mechanisms, and also the gradient of shrinkage between the surface and the core. But also, do not forget that we are working on reinforced concrete structures, and also that we have cement paste and aggregates. And we have an important mismatch between all the phases. So for instance, if you look at the scale of aggregates, so most of the times, except some light aggregates or natural aggregates. So you have almost no shrinkage inside the aggregates, only in the cement paste. So the shrinkage of the cement paste is restrained by the aggregates. So it gives rise to cracking inside the specimen. So you can observe it also here, and also by X-ray tomography. So here you have an aggregate and cracking, but also, of course, rebar is very good. Fibers are very good for concrete, but you have no shrinkage in rebar or in fibers. So you have a restraint also of drying shrinkage, autogenous shrinkage, also, of course, of concrete by the rebar, which may give rise to tensile stress and even in some cases to cracking inside the concrete. So heterogeneity also can be a strength, but also a source of trouble. So it was also the case of drying. So in order to give you some results, so I will present you an experimental campaign and some numerical simulations. So I will not give you all the results, but I will present an experimental campaign on concrete tie. So the idea was to predict the behavior of concrete nuclear power plant. With this use of data, we will try to model and to understand what will be the effect of drying. So here it's on a beam, but I will take the example of a concrete tie. And the idea is to develop a numerical model that can be used for structural applications, not too much parameters, and not also too much finite element inside the simulation. So the experimental test. So we used classical measurements, but also full field measurements. So what are classical measurements? So we need to have access to drying shrinkage, creep. We need to have access to mechanical properties, Young modulus, tensile strength, etc. But also to the link between concrete and the rebar. So we made also some pull-out tests in order to identify the law between concrete and reinforcement. And for full field measurements test, so we use two techniques. The first one is to use digital image correlation in order to have the field of displacement at the surface. But also we use optical fibers that has been glued inside at the surface of the rebar in order to have the evolution of the strain along the rebar. So you can see it here. So you have here cameras, lightning, and with the use of digital image correlation software Q4, which is developed by one of my colleagues in the lab, it was possible to have access to the crack openings. I will show you after some results. So 3 reinforced concrete tiles have been studied. So you can see the dimension, 10 centimeter by 10 centimeter, on more than 1 meter long. So we had only experimental result for two specimens. We had the failure of the measurement device during one test. The specimens were kept in autogenous conditions during 17 days, and after they have dried during 60 days. And for optical fiber, so we use optical frequency domain reflect techniques, which allows to have the evolution of strain along the rebar with a resolution of about a few millimeters. So the device has been developed by Agiat Kadour, so IFSTAR. So now it's University Gustave Eiffel. So for classical measurements, so we put here the results force with respect to the relative displacement between the concrete and between the rebar. So we have a classical law, so an elastic behavior. And after you have the creation of a crack, one crack, or as Dirk Schlicke said, multiple cracks. And after we have the propagation, and we have the yielding of the rebar, and then the failure. So in my presentation, I will focus on serviceability and durability, so I will stay here in this region. For full field measurement, so we have the possibility to have access to the evolution of strain along the rebar. So the rebar the behavior is elastic, so it's very easy to calculate with the steel strain. It's very easy to calculate the shear stress at the surface. But what we can observe, so here it was at the beginning before cracking. So forget here this dotted line. It is a numerical result. So just look to the experimental results. So normally, as Dirk Schlicke has shown before, so we should have a decrease, but here you have a small increase. And it was due because of cracking that occurred during the conservation of the specimen, so just without putting a force. And after, when you have cracks, so here it's coming for digital image correlation, I will show you after the results, you can see that you have a localization of the strain where you have these cracks. So you have, as Dirk Schlicke said just before, so the force in the rebar is going inside the concrete, but when you have cracking of concrete, so all the force is going into the rebar. So this cracking has been obtained by digital image correlation. So I don't know if you are familiar with these techniques, but the idea is very, very simple, but it's not easy to develop this type of software. So my colleagues are working since more than 10 years on that. So you have a speckled pattern in the surface, so painting with white and blue, and you are trying to observe the movement of this pattern at the surface of the specimen. So you will not look to the displacement of each pixel, but of a group of pixels. And with this type of techniques, it's possible to have access to the horizontal displacement and also to have access to the vertical displacement. So if you plot, for instance, so here it's along this surface, if you plot the evolution of the horizontal displacement in this line, so you have something which is linear, it is elastic, and after you have this typical jump, and this jump is corresponding to the crack opening. So it's possible very easily, after you have access to the displacement field, to have access to the crack opening in the surface. And this crack opening will be used in order to find out if it's possible to predict diffusivity and permeability. I will come back later on that, but it's also possible to use digital image correlation in order to master the boundary conditions, because people that are familiar with numerical simulations, the result is depending, of course, of the behavior of the material, but it's also depending on the boundary conditions. Most of the time, we focus on the behavior of materials, but if you do not know the boundary conditions, it's not necessary to do numerical simulations. So it's very important. So the model that has been used in order to predict the behavior of concrete structures is quite simple. So it's based on the damage mechanic model proposed by Professor Mazar, so 30, almost 30 years or 40 years ago. It's 40 years ago. So it's very nice model only if you have loading in tension. And in this case, for bending, for concrete type, it's okay. We have tension, we have also shear, but we do not have a mix of compression, tension, etc. So with this type of law, it's possible to calculate the crack opening. So it's not the real crack opening, but you can calculate the anelastic strain. So normally it should have been, so it has been removed. So if you are here at this point, so after you have the linear elastic behavior, and after you have damage evolution, so the softening. So if you calculate this strain, you know the elastic strain. So the difference with was what we call the anelastic strain. So normally it's not an anelastic strain because it's an elastic damage model, but it can be used in order to estimate the crack opening. So you multiply by this anelastic strain by the size of the element. And if you do this type of numerical simulations, you will see that your results will be mesh dependent. So in order to have mesh independency results, we use the regularization technique proposed by Hillerborg. So we just say that the energy, so the surface should be constant, whatever is the size of the element. So you have here the numerical results of bending for different mesh sizes. So you can see that it's okay. So it's in French here, elements. And since cracking is occurring where you have some flows, so you need to perform different, several finite element calculations. So Dirk was talking about Monte Carlo. So we will not do 1 million, 1,000 of numerical simulations, so just a few simulations. But since the material is heterogeneous, we use techniques in order to have random film inside the concrete. So it can be used to represent flows, to represent aggregates, etc. So it's a technique that is very easy to use, because if you want to measure the aggregates, the porosity, it's not possible. And you can perform after numerical simulations. So for instance, for the concrete tie, here you have the results for 3 numerical simulations. So you can see that you have different cracking pattern, and you have also sometimes different number of cracks, but they are most of the time similar. So first, the idea is to identify the material parameters. In order to identify the material parameters, so it's quite easy on concrete. You do test on concrete, and after you can identify mechanical properties of concrete. So here I will focus a little bit on the interface between concrete and rebar, because as Dirk Schlicker just said before, so in order to have cracking in concrete, you should have sliding between concrete and rebar. But if you want to mesh, let's say, for instance, a nuclear power plant, so the surface is like the surface of soccer playing ground, so it's quite complicated. So you cannot mesh all the rebar. It's not possible in 3D. So what we use for the modeling of the rebar, so just one truss element. But if you have one truss element, so it means that the nodes should be the same between concrete and between rebar, which is not correct because you should have cracking. So what we do, so we used volume around the rebar, and this volume is representative of the interface between the rebar and the concrete. So with this type of technique, you just mesh concrete in 3D, you mesh rebar in 1D, so it's quite easy to use for structural calculations. The most simple law that we can use in order to represent sliding is to use an elastoplastic law. So you have a linear part here, and after you have this plastic part. But if you look in detail in the rebar, as Dirk Schlicker just said before, you have ribs. So in order to be more representative of the effect of ribs, the idea here was to change the parameters between the ribs. So the idea, as you can see here, just here, is between ribs. So the behavior is quite complicated because between ribs you may have compression of this part, and it will increase the performance of the interface. And also you increase the surface of contact between rebar and concrete because of the ribs. So the idea is to modify some parameters. So here, for instance, the plastic strength, and also here the yielding. So depending if you are on the top or in the bottom of the ribs. So in order to show you what type of result we can have, so here you have the pull-out, classical pull-out test. The only difference here is when you do numerical simulation, as I said, you have to master the boundary conditions. So here we put a Teflon in order to minimize friction between concrete and this steel. So it's more easy to model. So if you plot here the evolution of the force or the bond stress with respect to the slip, so you have in black the experimental results. And here, for instance, if you suppose that you have perfect bonding, so you can see that it's not working. So you may have access to the beginning of the curve, but not the end. And if you use only one parameter, it's not possible to predict completely the shape of this curve. So of course, if you add one or two parameters, it will be better because you have parameters, more you will fit. I completely agree with you. But with this type of model, so it was better reproduction of bond strength with respect to slip, but also if you look to the damage, so representative of the cracking, if you use here this type of model, here you can see that you have uniform damage, but with this new model, you can see that you can retrieve what just Dirk showed before, so cracking appearing at the top of ribs. So it's not more complicated. Of course, you add some parameters, but you are more able to predict cracking. So we expect we are more able to predict cracking, but also we are more able to predict bond stress, sorry, versus slip. So now if we come back to the concrete tie. So in the concrete tie, so we have the evolution of the force with respect to the slip between the rebar and the concrete. So here you have the two experimental results. So if you do the numerical simulations, you see that you are overestimating the strength of the structure. Why? Is it a size effect? Because we know that if you change the size, etc., here in this case, the size of elements were not so much different, but it was not that, in our opinion. We were looking to the effect of shrinkage. So if you have shrinkage, so you have increase of mechanical properties or decrease, it depends. But you have also the effect that only concrete is shrinking, and the rebar will prevent shrinkage of concrete. So I will not go into the detail of the model because it's quite classical. So we have a partial differential equation in order to solve the drying problem. So you can use the capillary pressure, the saturation degrees, the relative humidity, whatever you want. So we assume that drying is much more related to the migration of water by permeation. We use the Biot theory in order to retrieve drying shrinkage evolution. And we use also creep models because if you, let's say as an example, you assume that here you have the completely restraint of concrete due to shrinkage. So if you have complete restraint, the total deformation is equal to 0. It's the elastic strain, the shrinkage strain, plus the creep strain. So if you assume very basically that the creep strain is proportional to the stress, you will find out that the stress is proportional to the Young modulus. So more the Young modulus is important, more the stress is important, the shrinkage, but also here you have the creep. So creep is negative if you are looking for deflection, for process loss, but regarding cracking risk by shrinkage, it's positive. And in this simple calculation, if the stress is higher than the tensile strength, you may have cracking. So it's also very important to have access to creep in order not to overestimate cracking. So if you do the numerical simulations, so here it's just before the application of the force. So you can see that you have already stresses inside the specimen. So here, if you have an elastic calculation, so without creep, and here with the take into account of creep, as I said before, if you do not take into account creep, you overestimate the stress inside the concrete. And you can see here that you have already a little bit of damage because of the restraint between concrete, shrinkage, restrained by the rebar. So now when you perform the numerical simulations, so you have here the experimental results. Here it was the previous numerical result. So we have overestimation of the load. And here, if you take into account shrinkage, you can see that you are able to predict more the behavior. And we have tested the effect of gradient because you have the restraint of shrinkage of concrete by the rebar, but also the gradient. You can see that the effect of gradient is not so much important, but it's quite, in our opinion, important in order to predict the behavior of concrete structures, to take into account the fact that you may have initial tensile stress inside the specimen. So this is for global information. If you look to local information, so that was the objective of my talk, you can see here that you are able also to predict here the evolution of the strain along the rebar. But here you can see that you have this jump, so we have already a crack that we had, if you remember, what we have predicted is not a complete crack, but also only some damage at the interface. So it's not completely perfect, but we have already some damage because of drying. So after, the idea was to predict durability, so the crack opening. So you may assume that for permeation, the Poiseuille law, so if you solve equations related to fluid mechanics using Navier-Stokes, you will show that the flux is proportional to the crack opening power 3. So here it's for, if you assume that the fluid is, the density of the fluid is constant. And here, if you want to predict diffusion, if you suppose that you have a model in parallel, you will see that the diffusivity will be proportional to the crack opening. So what I would like to compare in this specimen is the effect of permeability. So here the sum of crack opening over 3. So it was for permeability, and for the diffusion, so it is the sum of crack opening. So just be aware that you have it at logarithmic scale here, and here not. So for diffusivity, it's quite nice. So we are underestimating the sum of crack opening, but that's quite nice. And it was also the case, so a factor which is more important because you have the power 3 here. But the prediction is quite nice with the models that have not so many parameters. So we estimate that here it's possible not only to predict force versus displacement, it's quite easy with a lot of models, but we are also able to predict the crack opening. So now the conclusion. So I've shown you that with this type of model it was possible to predict some durability parameters. So sum of crack opening related to diffusivity and the sum of crack opening power 3 for the permeability, and also to reproduce the evolution of force with respect to displacement. I would like also to emphasize that the fact that in some cases it's important to predict the shrinkage, because as I've said before, it can be positive or it can be negative. Here it was negative, so in order to predict more correctly, it's important to take into account shrinkage. And also the fact that it's not only shrinkage, but also you have to take into account creep. So it's a little bit more complicated. Crack closure, if you have evolution of force applied, but also the interface. So it's not so easy to predict the behavior of concrete structures when you have evolution of temperature and relative humidity. In perspective, so I've shown you only 3 numerical simulations. So when you are looking to random calculations, normally it's 1,000, but it's non-linear calculations, so it costs a lot of time. The model is not possible to apply to take into account, for instance, confinement. You have some confinement, for instance, in nuclear power plant due to the press stress. So it's not possible with this model to predict that. Drucker-Prager criterion, for instance, can be used. And also, I've shown you that it's more or less okay to predict information in the surface, but as Dirk Schlicke said, so here it's from tomography, so it was a glass fiber, not rebar. So as Dirk Schlicke said, so you have an evolution of crack opening. So here it was in bending. That's why we have not the symmetry, and you can see that the crack opening is almost equal to 0 just after the mesh. So it's not only crack opening in the surface, it's also crack opening along the crack, also the tortuosity, because it will affect also the diffusion and also the permeation, and also the constrictivity, the branching, etc. So it's not so easy. So we have also a lot of work to do, but I would like to say that the use of X-ray tomography can be nice because you may have access to the crack inside the volume. Thank you for your attention.
So again, we have room for. I think there's no echo now. Yes. So.
Yes, thank you for your presentation. And I have a question about the influence of the loading frame. Yeah, in your analysis, it seems you model only the specimen, but the stiffness of the loading frame may also affect to the result. How do you think about that?
So it was for the concrete tie, or it was for the
No, yeah,
the pull-out test?
So
here is a concrete tie, and we also performed some tests on pull-out test.
Another one, pull-out test.
I'm not showing. Don't remember.
This one. Sorry, no, sorry. Not pull-out test, but the uniaxial tension.
The concrete tie. Okay.
Yeah.
So of course, it will depend on the rigidity of the machine, but here we have a cell in order to measure the evolution of force, and we have also LVDT sensor, and also we use digital image correlation. So we have the boundary conditions, and we are not using information that are coming from the loading frame.
Okay.
It can be important, for instance, in bending, for instance, in bending, so the loading frame, or perhaps also for stability of crack. It can be important, but here it's reinforced concrete.
Yeah, but I did similar test, and at the time, once the crack is formed in one side, it tried to bend. Then the rigid frame
okay.
also affected the crack.
Yes. I agree with you. So it will also depend here if you have the boundary condition here. So here we have a device in order to allow rotation of the device. And you can see that we for instance, the cracking pattern, it's not completely vertical, but it's quite nice. Perhaps this is not because of the rotation of the sample, but just because of the heterogeneity of the material.
Okay. I got it. Yes, thank you very much.
You're welcome.
Question? Side? But I do have a question. So now I have my microphone. So First of all, congratulations. Your work is always impressive.
Thank you.
And you're dealing with a very complicated thing with where too many things are interacting at the same time. I have to congratulate you also on the capacity to isolate things. But of course, my question will be a provocation, you know me. Because, of course, not putting anything in question, your specimen is 10 by 10, precisely this specimen that we are seeing. And 10 by 10, you left it 17 days in autogeneous condition and 60 days drying. So 60 days drying for a 10 centimeter specimen is not enough for the complete drying to happen. So the question is, did you then do the experiment in a very small time, but you have two tests, maybe they give you different results because one waited more than the other. And just to finish my question, when you are doing this, the moisture profiling within the specimen, is this something your models are accounting for? So can you comment a little bit?
Yeah, yes, I completely agree with you. So it would have been better, you know, to end the drying phase in order to perform the test. So without gradient.
In a perfect world.
Yes, in a perfect world.
It's not perfect. I know.
For 10 centimeter, so it's about between 6 months and 1 year.
Yes, my experience as well.
To reach the equilibrium. So it's not only numerical simulations, but it's also we have done some experiments. So we measure the weight loss evolution. So we did not at that time we did not put a sensor like you have done, you know. And it's better, I agree with you, to put sensors inside in order to capture the gradient. So okay, it's possible to capture a gradient using this model, but is it the
correct one? Yes.
I cannot say it's a good one.
Yes.
And that's why, you know, I put here effect of, no, it was just before, effect of size. So effect of size is not a size effect regarding tensile strength, etc., but it's also regarding drying. So it was not the same size, but by identification and after by simulation, we hope that we didn't make too much mistakes.
Yes, no, I'm sure you didn't. And this is the path to go in the right direction, in my opinion. We just need to do more experiments and we need to test and we need to find new generations of sensors that allows us to study things without intruding in them. My experience with measuring moisture inside concrete, we can do it, but it's so hard, so difficult to avoid artifacts. But congratulations on that. That's all I have to say. I don't know if we go to any more questions. Maybe the audience now is on fire or online. I don't know.
Before you start talk about the effect of cover depth, so now your cover is only 5 cents.
Yeah, so, less than 5 centimeters.
So if you change that such, you know, cross section, your model can simulate well.
We have a numerical model, so we hope that, you know, and it's you know, the purpose of modeling is to be able to predict whatever is the size of the specimen, whatever are the temperature and the relative humidity. So I cannot tell you, yes, it's working. I assume it will work. It will work.
Yeah. Okay, so to keep program, I would ask a nice applause to Professor Farid. Thank you.
Thank you. Thank you.
Thank you, Farid.
Thank you.
And the next speaker, Professor Nagai, will go. Correct? Oh, no, sorry. It was my mistake. My mistake. I was under the impression in the program we were switching, but now it's Agnieszka. I really apologize to all the audience. I have to call the correct speaker. Agnieszka, and I cannot say Jedeska or something similar. So from Silesian University of Technology. And she's coming to speak to us about the work in which I also have been partially involved about the codes for cracking. No, that's tomorrow. And today it's what? I'm totally wrong. I'm not looking at the program. So today is here you are.
Hello everyone. My name is Agnieszka Jędrzejewska, and as Professor Miguel said, I come from Poland, from the Silesian University of Technology.
She has to share again.
Yes,
maybe.
I need to share again. Yes.
And so today's prediction of crack.
Yes.
Okay. Should be, yeah.
Yes,
Perfect.
should be
Thank you.
working. Yes, so indeed, I have two presentations. So today's presentation, which is much shorter, it's a kind of a state-of-the-art overview of the topic that apparently we are discussing throughout the whole session. So it somehow wraps what has already been said by Dirk Schlicke, by Farid Ben-Bujema, and I guess in the next presentation. So just not to steal more time, I will proceed. So as you see, the topic of the presentation is modeling of cracking of reinforced concrete structures. And I would like to start this presentation with a bit of a comment about what we mean by modeling. So normally when we say modeling of concrete, we somehow relate it to numerical modeling, by which we understand computer simulations. However, in my opinion, the meaning of this topic is much broader, so we maybe should not misunderstand and misuse this word, because specifically regarding structural behavior or cracking behavior, of course, the modeling would relate to computer simulations of structures in which we implement what we call numerical models, so some mathematical models in a form which are understandable for the computers. But modeling would also relate to experimental testing, in which we are mocking up, so we are extracting some isolated parts of the structure to analyze some specific behavior. And even today, we have seen some examples of such experimental tests. For example, Dr. Luan had presented us such experiments of isolated tests on cracking. And finally, by modeling, we also understand using some analytical models, which are based on mechanics, which we use for example, for crack control design. So such a model was, for example, presented by Professor Dirk Schlicke, and also I would happily make a longer lecture on this topic tomorrow. So if you are interested, you're very welcome to come and participate. And nevertheless, during this particular presentation, I would like to concentrate on this commonly understood meaning of modeling. So I will be talking about computer simulations of cracking. And as I said, it will be a kind of the state-of-the-art overview of the approaches and important phenomena which must be taken into account during this process. So basically, we have two approaches to modeling of cracks, two general approaches. The first one is called discrete modeling. And in this approach, we have a discrete representation of cracks. And also, we need to remember that this approach is suitable to represent the behavior of some structures, or specifically structural elements in which we have few dominant cracks, usually with some predefined location and the direction of propagation. So this is an approach that is usually used to model experimental tests. And the other approach, which is much more popular, especially in more engineering-like applications, is the so-called smear modeling. So in this approach, which has been shown today, for example, a while before by Professor Ben-Bujema, the cracks are represented in a smeared manner, so they are not physical entities. And such an approach is more suitable in the analysis of typical elements in which we have a lot of cracks, which location is not known before, or which location we would like to define during the process. So a little bit more in detail about these two approaches. So as I said, in case of discrete models, the crack is a discrete localized phenomenon which has a physical meaning. It means that when we are analyzing such a structure with the use of, for example, finite element method, we are introducing a discontinuity in the mesh. So we are performing analysis in all the nodes of the mesh. And when we find a node in which the tensile capacity was reached, it means that the crack is formed in this node. We are introducing discontinuity in this node. We are remeshing our whole mesh, and we proceed to the neighboring node to see the propagation of the crack, and this way we are able to predict the path of the crack growth. However, as I said, this process requires remeshing, which is complicated, it's difficult, and of course it is computationally challenging. That is why in many applications this smeared approach is much more popular, because in such an approach the crack is not a physical entity, so we are not forced to introduce any discontinuity in the mesh. The mesh is fixed from the beginning, and we are just analyzing the stress state in the mesh. And how we approach this problem? In the smeared model, we treat the material as continuum, so it means there is no discontinuity. However, the parts of the material in which we reach the tensile capacity, so where we expect the crack to appear, they are assigned with some modified properties. So the material in these particular places in which the crack is expected are no longer isotropic, and usually such cracked element is divided into, let's say, a healthy part and damaged part. And we assume that in such a cracked element, this element can still transfer some residual stresses, but these are parallel or shear stresses, while the tensile stresses can no longer be transferred by the element. So the characteristics of such an element, which is partly healthy and partly cracked, are defined according to the applied material model and damage criterion, which I would like to now discuss in a little bit more detail. So first of all, we need to define that the crack potentially appeared in an analyzed element. And the simplest method to do this is to use the cracking index, or something that we can relate to the cracking index. However, I don't want you to mix it with the thermal cracking index that we have in the JCI guideline. Nevertheless, such let's say, a name appears in the literature. But as you can clearly see from the equations which I show, this is a procedure in which, depending on the approach which we use, so either a stress-based or strain-based, we are relating the tensile strain or tensile stress to the tensile capacity of the element. And I would say that the main challenge in this process is the definition of the effective tensile capacity. So the value of tensile strength where we say that cracking appeared. But I think this problem has been discussed a couple of times today. So this is just to mention the problem. And then once we know the cracking have occurred, we need to define how the element which is cracked or partially cracked in some places would behave. And for that, in the simple case, we use the damage models. So the damage models, and this is the case that has been presented by Professor Bembujema, these are relatively simple models which we can use, assuming that concrete behaves well in compression. So in normal cases, it's really hard to reach compressive stresses which would destroy concrete in compression. But we have very or relatively low tensile strength, so the damage to the concrete would be induced due to tension. And due to tension, the concrete degrades. So as I said, in such damaged models, we assume that part of the element is sound, it is healthy, and part is cracked. And this healthy part is still able to transfer some residual stresses. And we are modeling this behavior with use of the parameter which we call the damage. And this model has been fairly well described during last presentation, but just to remind you, we have this damage parameter. So as you can see from this very simple formula, if the damage is 0, so the element is not cracked at all, then the element can transfer stresses fully. And when it is entirely damaged, it is no longer able to transfer stresses. Everything in between, this is a residual stress to be transferred. So this damage parameter, as it has already been said, describes the behavior in the element in tension. And this is defined by let's say 2 ranges of behavior, which has been shown. And just on an example of the model which is proposed by model code, but of course there are many models of such type, but they agree that in tension the element behaves more or less in an elastic way. For example, the FIB model proposes this bilinear relationship. In case of Farid's presentation, it was just 1 line, but of course this is subject to choice to discussion. And then once the element is cracked, we are observing the softening behavior, which is related to opening of the crack. However, the use of this model directly is not very feasible because we don't really have a crack, which is opening. That is why we are operating rather with the use of the so-called crack strain, which has already been discussed as well. So using this crack strain, we are able to recalculate the crack width, knowing the value of this crack strain and the size of the element, and also to avoid the problem of mesh dependency. We are using this parameter, which is called crack bandwidth or characteristic length. And this is a parameter which is related to the fracture energy. So it's one of the, let's say, inherent properties of the material that we are studying. However, we must remember that the damage models are mostly suitable to one-dimensional analysis. So the cases in which we have one direction of principal stresses, in which we have this dominating tensile stress, but also, as Farid mentioned, it is not really able to deal with the multi-axial stress states. So in case we would like to deal with some multi-axial stress state, we need to use some more complex failure criteria, and such failure criteria are usually defined in a general form for three-dimensional stress state, and they are defined in the space of principal stresses. And as I said, with such formulations, we can study 2- and 3-dimensional stress states of any kind. Such failure criteria are usually represented graphically with the use of the so-called failure surfaces. And such failure surfaces, for not only for concrete but for different materials, have been developed for over 100 years as of now, from the simplest 1 2-parameter criteria through 3, 4 or even more parameter criteria. So as with everything, the more we progress, the more complex these solutions become, because we believe that the more complex they are, the fuller is the approach that we can represent the behavior. But this topic is so broad that I believe I could make a lecture just about the failure criteria alone. But what I wanted to say as a key takeaway from this lecture is that such a failure criterion, not only for concrete but for every material, is usually defined based on some specific strengths of the element. So usually it is derived based on uniaxial, biaxial, and triaxial compressive and tensile strength, which are characteristic points lying on the surface. And what we know about concrete for now is that when we look at such a failure surface, we know that the axiatoric section, so let's say a cross section of such a surface, is not a circle, and it's not a shape, it's not a figure of revolution. And also when we look at the deviatoric section, so let's say a longitudinal section, we know that the lines, the meridians of such a failure failure surface are not straight lines along the whole surface. They become somewhat slanted towards the area of tensile stresses, which is so depending on the criteria. This is either represented by introducing curvilinear meridians or combining the straight meridians with some form of a cap that closes the surface in the area of tensile stresses. Also, it must be remembered that such a surface can be used to define the shape of the yield surface. And in that case, we also need some cap, so some limitation on the side of compressive stresses. So if we have this full definition of material model together with failure criterion, this would allow us to produce a full representation of the material behavior in form of such a failure surface. It is also important to mention that such failure criterion represented with failure surface can be defined also for hardening concrete, and in a quite easy way, because as I said, such a failure surface is defined by some specific strengths, so some specific mechanical characteristic of the material, and we know that they are changing in time, or more precisely with the progressing maturity. So also we can define the change of such a surface in time or with progressing maturity, which would exhibit a behavior of like swelling of such surface with respect to some fixed starting point. And now relating to the material model, so I would like to briefly explain how to understand the use of this failure surface with respect to the material model. And this is on the example of material model for concrete, analyzing compressive part of its behavior. So we know that while the concrete is within the elastic stage, so the point of stresses which represents the behavior of concrete is inside the yield surface. Then when it reaches the plasticity limit, it means that such a point is exactly on the yield surface, so it reaches the yield surface. And then by the definition of the flow rule, we would know how such a yield surface would behave. So for concrete, we usually use the isotropic flow rule, which means that we can imagine that such a yield surface would be swelling with a specific rate until it reaches, so it coincides with the failure surface. So this is this ascending branch. And when the two surfaces like touch each other, so cover each other, it means that we have reached the ultimate capacity. So we have reached the strength of the material, and it means failure. And then what becomes after failure? This is defined by this damage model, which I explained before. So it will tell us how the failure surface would behave after damage. So after the point representing the stress state coincides with the failure surface. And as I said, depending on the location where this point reaches the surface, the failure is manifested with different modes of cracks. So the mode which is most interesting for us is the mode in which we have a splitting crack, and such a splitting crack is formed when the point representing stress state reaches a failure surface within the zone of tensile stresses. However, we have also different cracking models. So apart from the splitting crack, which is the opening mode and which appears when the tensile stresses are more normal to the plane of the crack, we also have a shear crack. And we can have a mixed crack in a tearing mode when we have a complex stress state. However, as I said, for us in our research and in design, we are most interested in the splitting cracks. So just to show you an example of modeling of cracks, this slide presents a quarter of a wall. So this top part represents a wall on a foundation, and the wall is subjected to heating and then progressing cooling during the hydration. And this type of the element is quite a nice example in which we can use damage models. So where we can find a correlation between the principal stress and tensile stress, because we can see that in the cooling phase, when we have tensile stresses, the principal stresses are mainly located horizontally. So the horizontal stress coincides with one of the principal stresses. And as I said, the crack is formed in the direction perpendicular to the main tensile stress. So knowing the location of principal stresses, we can indicate both the location of the crack and also the direction of its opening. And the final aspect, which is important during modeling, is of course related to the bond between the reinforcing bar and the surrounding concrete. So this is also a topic which has been discussed quite in detail. And just to remind you the figure which you have already seen from Professor Dirk Schlicke, just a reminder of what happens in the element which is cracked. So we know that when the crack is formed, we have incompatibility of strains in steel and concrete in some vicinity of the crack until at some point the compatibility is reached again. And this length over which we experience this incompatibility is called the slipping length. So of course, the length of this slipping length would depend on the bond properties between steel and concrete, specifically the bond stresses, which depend on many factors. And these factors include, of course, the type of loading, the properties of concrete, such as its strength, the concrete cover, casting position, some properties which are related to the reinforcement in itself, like its mechanical properties, diameter of bars, spacing of bars, surface condition of the bar, so whether we have, for example, plain bar or a ribbed bar, and whether we have any means of confinement in a form of, for example, transverse reinforcement. And also something that has been widely discussed by Professor Schlicke is that usually in simplified calculations, we use the mean value of bond stresses. The most common value is 1.8 tensile strength of concrete. However, as it has already been demonstrated to you very well, the bond stresses are dependent on the value of slip, and only if we are including this in calculations, we can really predict the crack, so the number of cracks, whether one or more cracks would form, and what would be their final width. To do so, we need to introduce the bond law, and